In this video, we're going to be taking a look at 3.4, modeling data patterns. This really isn't any different than anything that we've been doing. We're still looking at the same sort of ideas. So for example, we're going to read this first paragraph. In many real-world problems, it is impossible to find an equation that fits the given data exactly because we live in a world that is messy. Not everything works out perfectly. However, everything is predictable. Even human behavior is predictable, right? So for example, consider the table in the graph below. They show the bridge experiment data collected by a group of students. We've done this. This is one of the first things that we did in this particular unit. So you have your length and your bridges here, and then how many pennies it took to break those bridges or cause them to collapse. And on the right hand side, you notice we have the data. So right here's the breaking weight, or how many pennies, and then your independent axis, your x-axis, your horizontal axis, that is your length in inches. Okay, so these here you have your table, and then your table, and then your graph. It's the same data presented two different ways. Some of the questions we're going to try to answer here, it says, do the data suggest the relationship between, does the data, that sounds better. Does the data suggest the relationship between length and breaking weight is linear or an inverse? Ooh, that's tricky. That's tricky. What equation would model the relationship well? These are the questions we're going to try to answer in answering these questions down here, A through D. So, problem A says, what do you see in the table and the graph that suggests an inverse variation relationship between breaking weight and bridge length L? Go ahead and try to answer that question on your own if you haven't already. Pause the video and then come back. So on A, what makes it look like an inverse variation is the fact that the values decrease at a decreasing rate. Meaning, you know, from here to here, then here to here, then 19 to 17, 17 to 15. At first, it decreases by almost 20. And then back down here, it decreases by almost 2. So much less. You can even see that huge jump from there to there, and then smaller jumps as you go along. So to me, looking at those trends, that's what makes it look like it may be an inverse variation relationship. Now let's take a look at B. What value of K would make the equation K equals W times L true for a length of 4 inches for a length of 6 inches? Right, so we're looking for that value of K. Think about what your equation would be if we were trying to find that constant, and if it is an inverse. So to answer B, we are saying that this is an inverse relationship. So think back to, hold on. There we go. Think back to what that equation was and how we found our variable K, and then answer that question. Pause the video, try this on your own, and see how you did. So in fact, they give, I didn't see this, in fact, they give you that constant relationship. So it's the weight, the pennies, how many pennies, that's the W, the breaking weight, times the length. So that's even easier. So if we want to find K for when the length is 4 inches, all we do is come up here, right here. So we know that it's going to be the breaking weight times the width. So K is equal to 4 times 41, which is 164. And then for 6, K is equal to 6 times 26, which is equal to 156. So that is our answer for B. We know that for 4 inches, it's going to be 4 times 41 and that is 164. So our equation would be 164 is equal to length times the breaking weight. And then here for 6 inches, it was 6 times 26, and that gave us 156. So then if we were to write an equation for that data, just looking at that particular data with the 6-inch bridge, it would be 156 as your constant is equal to length times width. All right, and then on C, what equation is a good model for the function relating the weight to the length? Now, in order to answer this one, let's find the rest of these K's on this one. And we can find 3 more equations and then maybe look for the average constant throughout. So go ahead and pause the video and try C on your own. Okay, so if we look at this one, we're finding the rest of them up here. So we've already found what if the length is 4, 6. Now we're looking, what if the lengths are 8, 9, and 10? And that's just looking down in our graphs right here and multiplying by the breaking weight, because that's how we find our constant. That's our equation, is the breaking weight times the length, right? Because we know that they're most likely inversely related. That's the assumption we are building all of this off of. And here are all of our constant values. Now, to get a decent equation, let's average these. If you were to go through and average them, what would be the average of all of them? Because he says, what equation is a good model? So go ahead and average them if you haven't already to see what that would be. And when we add all of these together and average them, you get 155. So you take all of that divided by 345, you get 155. Okay, so that is our average constant value. So really any value in between 150 and 165, because, or 164. 165, yeah, 164, that was our largest. Any between there, but if we average them, it's 155. So a great equation would be 155 is equal to length times width, or sorry, breaking weight. And that would give us a really good graph that would go through the majority of those or somewhere in the middle of those. And so that's the equation that we would want to use if we wanted to predict, right? Which is what we're doing in part D. We are predicting the breaking weights for 3, 5, 7, and 11, which you notice are not on this chart up here. 3, 5, 7, and 11 are not on that chart. So go ahead and do part D using this model right here to predict those other lengths. Okay, and then if we look at all of those breaking weights, here are all of your equations. The first one is 155 is equal to the length of 3 times the breaking weight. 155 is equal to 5, 7, and 11. And remember, we use the fact families. We know that 155 over 3 will give us W, and that gives us 51 2/3 pennies. Label your answers, please. 155 over 3 is equal to 31 pennies when the length is 5. 155 over 7 is equal to 22.414 pennies. Obviously, we would round that down either to 2 or up to 23, but right there's the exact answer. And then 155 over 11 gives us 14.09 pennies for your breaking weight. So it breaks somewhere between 14 and 15. Statistically, that's where it should break. Real life, is that exactly where it's going to break? Not necessarily, but if you were a betting person, that would be where you would place your bet, between 14 and 15 pennies. But we don't bet. All right. So this is our notes for 3.4, modeling data patterns. And that is it.